will start today's section. I hope I'm audible. If I'm audible, please give a thumbs up.
Yes, ma'am.
Yeah, thanks. Okay, right. First, we'll start off with our lecture 1 of module 3. So, in this lecture, overall, we are going to see some of the basics of transfer functions. Why, how, and what about transfer functions, and then how to define or how to find a transfer function for any system, any real-time systems. And with this transfer function, what we can do in the later lectures that we will discuss only. And then we'll discuss about the stability of the system in terms of its transfer function representation. This is the overall content we are going to cover in this module, module 3. So by this end of this session, you should be able to represent a system using its transfer function, how to connect its input, output, and the system behavior, and how to derive the transfer function from the differential equations. And you should be able to interpret what are poles, zeros, time constants about the system based on this transfer function representation. Right. When you press the accelerator in a car, why doesn't the speed instantly jump? Can you think of it? So you have a car, and we'll be riding this car. Let's say this is facing this side. So you have an accelerator here. Uh, from the start, it's a 0 kilometer per hour. So when you press the accelerator, maybe you press it with the full force. It doesn't jump from the maximum lowest possible to the maximum possible. Let's take this is the maximum capability of the car to move, speed of the car to move. Okay, it doesn't jump from 0 to 100, right? It takes some time to reach this value 0 to 100. Then it, if you keep on pressing on the accelerator at the same force, it will try to keep it in the 100 kilometer per hour. So this period of time, it's there, no? It's same for fan also. So when you switch off your fan, this is a very bad representation, but that's okay. So when you switch off your fan doesn't go straight away from stopped position to the instant maximum RPM. It takes some time to increase and reach the position, and even when you switch it back, switch it off, it will take some time to reach to the stop position, right? The reason behind these things is the system takes time to respond because it has some inertia and damping. So we are taking this time of response because the system has its own inertia and damping. The force you are giving has to overcome this system's inertia and damping. That time it is taking to reach to the maximum output or whatever desired output. So this transfer function models how the output reacts to the input over the period of time. This is what the transfer function is. So your transfer function will model how your system output responds to your system input over a period of time. So we are going to study this one, this transfer function we are going to study. So for each system, how the output responds to the input we are giving to that particular system over the period of time. This is very crucial because when you want to design a controller, you need to know the system behavior. Only with input and output, it's not possible to control a system. So in that case, we need this help of this transfer function. Okay. First, if you see in this thing, you will see there are different kinds of inputs. They used impulse, step, both has been used here. Other than this, we have another two inputs that are ramp and parabolic signals. So if you would have studied systems or signals and systems, this you will be familiar with this. Otherwise, there is a short introduction I want to give for this signal. So these four are very standardized signals we use in our control system. domain. So for example, why we are using the signal is that these are all some standardized signal. If people want to use their own signals by like whatever they want, that doesn't come under a standard, and we cannot standardize the way of representing a system, right? So control system people have come up with some 4 different standard signals so that each can be used for different purposes. For example, this impulse signal represents the sudden increase in values. Whatever signals that has a sudden increase in values, for example lightning in real time, can be represented using this impulse model signal. And next type is a step signal. Step signal looks like this. Until 0 it will be 0. After 0 it will have some value, some t1 t value, so for a period of time. So it will be constant after the 0th period of time. So this is equal for any real time system. For example, if we switch the fan off on, so until then the output or the fan won't rotate. So after it, this input keeps on, the switch keeps on, so the fan will tend to rotate until we switch it off. So this is a example of a step signal. Or we have a ramp signal where we keep on increasing the um, input until we reach a certain point. This is an example for a car accelerator. So a car accelerator can be modeled as ramp and also the step. For example, I am starting from 0 and goes up to 20 kilometer per hour, and I am maintaining it 20 kilometer per hour. So until this it becomes ramp, and after that it becomes step. So the fourth signal model is the parabolic signal. Parabolic signal looks something like this. It's a curvy or exponential. So generally this is a parabolic signal. So it can be a rising or falling exponential. So whatever these are, so far we have been seeing the straight line models, right? So these are all like straight line models. If you want to make it little complicated and make the system looks exponential, then you can go with this parabolic model signals. So these are a more standardized way of representing a signal for a system. So this is like mimicking the real-time input signals in 4 ways, so that we can model the real-time signals using the standardized signals and say, oh, this is how the system responds for the signals. So we have used this impulse and step here with disturbances. In control system, disturbance refers to a perturbation. Perturbation means there will be an input, there will be a system, so output will come. Until we don't touch or any externally it was not changed anything, then this is an ideal system. So disturbance in the sense we are injecting something externally. For example, it may be a process, it may be a sensor noise, or it may be a external change in the parameter of the system. Whatever way it is affecting the ideally operating system state, it is considered to be a disturbance or a perturbation, whatever we can call. Both represents the same thing. So they are adding on disturbances. Disturbances can be anything, you can assume anything. So far we are not disclosing anything, just some disturbance, some external parameters we are adding. So these are all the response to the system. I'm giving an input system, I'm giving an input and output. I will share actually that another scholar, he was new, and I was in a business trip, so for a conference I couldn't come online. So we'll share the link. So he doesn't know how to add those things. I will help him and we will make that link online. Okay, great. So we have been discussing about this current. So we have taken one input. First impulse input we have given, kind of this signal we have given, and then step input we tried, and both inputs with some disturbances, some external disturbances. Like if this is a 5 unit, I would add some 10 units. That's another disturbance. Or if it is a step signal, I would add something, some 0.12 waves. I'm adding some kind of disturbances I'm adding into it and taking the response out of the system. That's what it was given here. Similarly, this is for some other system. This is for system 1, let's take. This is for system 2. So these are all the two different output responses for two different systems. What we are inferring from it, that was the question. The next thing is, what causes the system to respond to signals in a certain way? What could you think of? Why two different systems are giving two different output? Obviously, it has to be, otherwise both systems will be same. But why particularly in this way, you think? See, this is giving something around 0 and this is giving something around 1.2. There was a huge difference in the responses, right? It is like exponentially falling everywhere, but this is exponentially rising and coming to a stabilized point. So the answer to this is, it's based on the system's nature. So in this nature we are going to study now. So what kind of system will produce this signal, or what kind of system will produce this kind of signals, or is there any way to standardize these things so that I can say, so first order system will behave like this or second order system will behave like this, to come to a box, to put everything inside a box so that it will be standardized. Is there any way to study those systems? That's what we are going to see so far. Right. Now let us take a circuit with only the resistor. It's a very simple system. You know, resistors cannot hold memories, right? Resistor is a memoryless system. It cannot store energy. So there will not be any memory from the past. It's like, for a resistor, if you give some input, it will give some output. That's it. It will resist the voltage flowing across it. It has some resistance. So its nature is to oppose the voltage flowing again across it. So that's what the purpose of the resistor is. It doesn't store any energy, or it doesn't have any elements to store. Right. So we already discussed the Ohm's law, right? V equal to IR. Whenever we are considering a resistor, the voltage across the resistor is the resistance into the current passing through it. So this just directly gives the relationship between the resistance and voltage and the current in that particular circuit. So V can change with respect to time, I can change with respect to time, but resistor is a constant one, so it's a static resistor. There are variable resistors also, but here we are considering only the static resistance. Only V and I are changing with respect to current. So here we are using a Laplace transform. I hope you would have studied this thing in week 2 content. Let me just confirm whether we have it in week 2. Did you study Laplace transform in week 2?
Yes, ma'am.
Yeah.
Yes, ma'am.
Okay. So you know the basics of Laplace transforms, right? Now, Ayush, I think somebody is knocking. Please. 1 minute. Okay. Using the Laplace transform, we are going to, we are just going to take the Laplace transform of it. Since it doesn't have any memories, we are straight away writing it in terms of S, V of S into I of S, where if you want to, voltage is the input here, current is the output here, right? So whenever you are giving this voltage to the resistance, you are getting this much current. So the voltage is input, current is output here. I am writing in terms of output by input. It will be V of S, I of S by V of S is equal to R. So whenever you are writing Laplace transform of output by Laplace transform of input, then you call that as a transfer function. This is the official definition of the transfer function too. So when you want to represent a system, first you want to find the S domain of the system. So how the system will look like in a frequency domain or S domain, particularly with real coordinates and imaginary coordinates. Then if you write it in terms of output and input in its S domain, then it's the transfer function representation of the system. Simple, straight away method. Clear? So if you want to write a transfer function, or if you want to find a transfer function of a system, first find the Laplace transform of the output and the input, then write it in terms of Laplace of output by Laplace of input. Then that is a transfer function representation. We will work out on this with few examples. Okay. I guess if I put I by V, it will be 1 by R, right? Nobody has pointed out this. Okay. Then this is the transfer function of the system. Okay. Now we are adding some dynamics. We are adding some spice to the story. So far it's a memoryless system. Only the R I have. Now I am going to add one L, which stores energy. So now we see how the system will behave. Right. This is my R, this is my L. I put L in a series with respect to R. Now I am going to write the same equation. Before that, when the L was not there, it was like V of t is equal to I of t into R, right? This is just the Ohm's law, based on Ohm's law. Now, since there is another element in the circuit, series circuit, I am going to use KVL, where in the previous lecture itself we saw KVL tells all summation of all voltages in the system will be equal to 0. Or we can also redefine it as sum of the voltages coming to a node and some of the voltages leaving from a node will be equal to 0. So when we want to write this, it will become minus V of t plus R plus L di by dt equal to 0. This will become V of t equal to R into R plus, sorry, I into R, right? So IR plus L di by dt. If you want to take a Laplace transform of it, this will give me I of s into R plus di by dt becomes s, right? So it will become Ls, L into S, because the differentiation of I di by dt will become Laplace of I of s into L into S. So this will become S into I of s. Into L, there is L is a constant, it is there, into I of s. If I take I of s constant, this will become R plus Ls. The left hand side becomes V of s. Now if I want to write it in terms of output by input, I of s by V of s is equal to 1 by R plus Ls. So this is the transfer function of the system. Now what is the relation between transfer function and order of a system? How will you interpret this? So first thing is, order of the system can be defined in two ways. One, I can say physically, it's a energy storage element, number of energy storage element in the system. Otherwise, if I want to say, I can say the highest degree of the denominator in the system. Mathematically, this is like, physically it's a highest number of energy storage element. Mathematically, it's a highest degree of the denominator of the transfer function. So if there is a transfer function, for example 1 by s square plus 2, then the highest degree of the system will be 2 right here. Then I can say there are two energy storage element in the system. For example, when I say the R system, R circuit, the transfer, what was the transfer function? V of s divided by, sorry, I of s divided by V of s is equal to 1 by R. Is there any S here? S term here? R is a constant. It doesn't have any S term, right? So there is no parameter or value here. It's just a constant. So the degree is 0. I can say the number of energy storage element is also 0. For example, in RL circuit, we got I of s divided by V of s is equal to 1 by R plus L. Yes, so L comes here. So highest degree of the system is 1. So the number of energy storage element will also be 1. Similarly, if I write RLC circuit, what do you think would be the order and the number of energy storage element? Is C an energy storage element?
Yes, ma'am.
Okay, then the order will become 2. Yeah, there will be an inductor and capacitor. 2 will be there. So let us just write the equation for clear to make it clear. So this will become I of t into R plus L di by dt plus 1 by C integral I of t dt. That's how we write the voltage across the capacitor. So this will become when I take a Laplace transform, this will become V of s, I of s into R is a constant, L is again a constant, Ls into I of s plus 1 by C is a constant. Differentiation we add S, integration we add 1 by S, 1 by S into I of s. So if I take I of s is constant, R plus Ls plus 1 by Cs, V of s. Writing in terms of output by input, Laplace of output by Laplace of input, this will become 1 by Rs, R plus Ls plus Cs. Sorry, 1 by Cs it is. Right? So just rewriting it would give me 1 by LCS square plus RCS plus 1. So this would be the final transfer function of a system. So here you can see the highest degree is 2. So the energy number of energy storage element will also be 2. So there might be questions like this. So for a one word it will be easy for us to ask, right? So if we will give a system and we will be asked to find the transfer function and ultimately find the number of energy storage element. So find the transfer function and see what is the highest degree of the system and answer the question what are the value you are getting for it. That's it. Right. Now, this distinguishingly changing the system from one point to another point. When it was RL, RLC, so 0 degree, first degree, second degree. So this order will also be same, right? So this is a zeroth order system. This is a first order system, and this becomes a second order system. So in general, we have systems natural classification until second, and rest of the orders we call it as higher order system. That's it. So we have distinguished explanations or classifications or behavior modeling for systems until second order in control systems. After that, we go whatever orders we have 3, 4, and until n order, we call it as higher order system. And right after this, it will become non-linear system. So it will be either we will linearize it around an equilibrium point and see the stability. Otherwise, we will consider it as a non-linear and use non-linear tools to deal with it. That's it. So for now, we will start from the baby steps. That's from first order system. We can also use this with different examples, whatever we saw in the first few weeks, like mass spring damper systems and all. So that will also be a second order system if you want. And another example, it was given in the PPT's DC motor example. That's also an example for a second order system. Right. I want to show the MATLAB plot for the different systems so that you can visualize it properly. Let me share my screen. I'll join from my PC. this is the step response of a first order system. For example, I have considered 2 as a resistance value and zero point 0.5 as an inductance value, and found the transfer function. I can show that what the transfer function is. G first I'm considering, it will be G1, this will become G2. Okay, right. Why both are looking same? I think something is missing. Okay, right. Step of G1, step of G2. Yeah. So this is figure 1. I guess it's better to okay. Right. Now see. So this is the G1. Uh, G1 you can see it's 1 by 0.5 S plus 1. It's 1 by R LS. L is 0.5 plus R is 2. So this is the response of the system for a step input. Step input reference is 1, but it is settling at 0.5. We don't do any changes or any control here. Just we are giving an input to the system as 1. It is supposed to track 1, but it is giving based on the nature and the response of resistors and inductors value, choosing the nature of that value. It is giving the settling is at 0.5, so there is a 0.5 deviation from the settling set point. That's okay. Right now we are not bothering about it, but it has this kind of response. It is slowly rising and going to the point and reaching there. So when I run the second order system, so this has this kind of response. And if you see, there are S square where it is L, I think it is LC. L into C, it's 0.05, where L is zero point 0.5 and C is 0.1. And the second term is RC, 1 into 0.1. And the last term is 1, that is R. So this is a second order system, and the nature of response is like this. It has some overshoot and some oscillation, and it takes time to settle. So these two, from this you can say, so this is a response of the first order system and second order system. Second order system can also respond like this. Only from this curve you cannot come to a conclusion that it is a first order or second order. But from the transfer function I can come to a conclusion this is how a step response should look like. So for the first order system, this is the exact response you will get it. You won't get something like this. This is the difference between how a nature of a system will vary with respect to adding the elements. So if we add some energy storage element, for example, I have added capacitance here, that change the nature of the system because it added one degree, or it added some of the, it changes the behavior of the system, dynamics of the system, so the behavior also has got changed. So we will closely look up what is first order, what is second order, and what is the major difference between these two. Right. Next is right. So we have some different kinds of inputs. As we told, like impulse response. What is impulse? We are going to see one signals one by one. So impulse response will be whatever value we can consider some t. Mostly, if it is a unit impulse, this t will be equal to 1. Otherwise, whatever impulse value we are considering, it will be there only at t equal to c. When t equal to c, for example, if the lightning occurs, it occurs at that particular second. That's it. It maybe it won't also not be idealized into that particular second. It might take some microseconds, milliseconds, but we are broadly considering it as quickly it is happening, right? So at that particular second, it is coming and it is disappearing. That's it. That's an example for it. So at t equal to 0, the signal will exist. It won't otherwise. That's it. So we can represent this using the symbol delta t, where it will be 1 when t equal to 0, 0 otherwise when t not equal to 0. That's it. So this mathematically represents the nature of the impulse signal. Similarly, we have step response. When until 0, it will be 0. After 0, it will have some value. So it also looks like a t signal only. So for t, if the t equal to 1, we call it as unit step. Otherwise, it's just a step signal, whatever value we have. So this is for unit step. So I'm telling at t greater than or equal to 0, it will be 1. When t less than 0, it will be 0. It's a just positive signal, and you can say it is a causal signal most of the time, because we don't rely on future or anything that you can think about it, whether the step signal is causal, non-causal, static, non-static, or dynamic, kind of, right? So if you take a Laplace transform of this, you will get 1 for impulse signal. So we will make a table here. Impulse, how we will define is delta t, unit will be u of t. Similarly, two other signals we have, that is ramp and parabolic. Ramp will be considered as r of t, parabolic is p of t. So this will become, when you take a Laplace transform, this will become 1. For this will become 1 by s, 1 by s square, 1 by s cube. And also we have some intricate connection between this. For example, impulse step, this is step, impulse step, ramp, parabola, right? So we have 1 by s, 1 by s square, 1 by s cube. So when will you get 1 by s? So in that unit step, when we see, there was L di by dt. So when you have a differentiation, d of I by dt, when you take a Laplace transform, it becomes L into s, right? S into I of s it becomes. So when we have a differentiation, we have an s. So when we had an integration 1 by c into I of dt, we had 1 by s. So whenever we have integration, when we take a Laplace transform, it becomes 1 by s. So here 1 becomes 1 by s. So what would have happened here? There happened an integration. So when we integrate a impulse signal, you would get a step signal. There is a integration of, I can explain it like this. There happened a integration operation. So mathematically or logically, how can we tell this? So if this is an impulse signal, I am integration is like adding part of it with respect to time, right? So I am adding some integration, some impulse signal over a period of time. So this is a integration. So this becomes ideally a continuous signal. When t equal to 0, this become a impulse. So ideally, if I keep on adding this, it becomes a step signal. That's how the integration comes into the picture. So impulse, if you integrate, it will give step. Step, if you integrate, it gives ramps. Ramp, if you integrate, it gives parabolic signal. On the other hand, if you differentiate parabola, you get ramp. Differentiate ramp, you get step. Differentiate step, you get impulse. So this is another intuitive concept you have to keep in mind. Please don't get confused about the integration or differentiation. Keep this things in mind. So if we integrate or if we add impulse signals, it becomes step, right? So the first step is, if we integrate, it will give step. Rest of the things you can come or you can get from that. So I hope this is clear. If you have any doubt in this, please ask me, because this is an important concept. Many questions can come in this. I will give you some moment to think about it. If you have any doubt, please ask. Clear? Can I get some thumbs up? Aditya, Ashmil, Sayantan, Gayatri, are you with me?
Yes, ma'am.
Rest of the people, you're okay or you're not okay, you're not agreeing. Okay. Ashmil, Aditya. I think both are not here. Okay, we saw this examples, first order, second order examples, and DC motor you work on yourself. And if you have any doubt, get back to me. I'll explain. And this cascade is just putting two systems in series. How the input and output of input of the output of the first system affects the second one, and we have same in parallel how it will become add on. So if we put in a series, it will become a multiplication. The transfer function of the first and second will be multiplied together, and if we have both system in parallel, it will be added or subtracted together based on the signs of the signals. That's the difference. And we have a feedback. We have seen this in a closed loop system representation. The only new thing here is a E of S, where E of S is the difference between the output and the input. That's it. So this is the representation of a closed loop system. It's very important with negative feedback. So as I already said, the negative feedback, though it is negative, we have been using it very particularly in control system, because most of the cases in real time system we will get a negative feedback. If we get a positive feedback, then it becomes a oscillatory system, so we are not interested in that, so we mostly use negative feedback systems in our course. Good. And yeah, you can try by yourself. Just we have given some example MATLAB plot, so you can play around with it by changing the values from t to t0 to t5. If you give like this kind of responses, you can get. If you can give step response from 0, or you can just start your step response from 1, until then you can make it 0. Otherwise, the ramp and step. So change the combination and play around and see how well the nature of the system changes. Fix one system and change the input behavior and see how how the output response changes. It's just a practice. Okay. So DC motor transfer function. Mm. These are all some important things. You would expect this in exams, because these are some practical examples. For example, you can prepare like, you can practice the transfer function of DC motor, pendulums. These are some classic examples. Cruise control. So by doing this practice, you would get to know how the system behaves with respect to the order. For example, this DC motor would be a second order system. This pendulum can be first order or second order based on the friction you are considering. Cruise control can be a second order system. So, based on this, you will identify. Sorry, it's a first order system. Based on this, you will identify how the system, a real time system, how we can connect between the real time system and the mathematical representation for the same. So go through these examples and try yourself by solving these examples. Write a differential equation of that example first. Differential equation is the mathematical representation of the system based on the element presence in the system. And try solving mass, spring, damper. We have a rotational system where we have inertia, theta dot, angular position, angular velocity. So these are some examples that involves that. Electric circuits R, RLC, RL, and maybe RL parallel circuits, RLC parallel circuits. These are series and parallel circuits you can try. And gears, system with gears. So we have another term called gear N1, N2. So this is added terms that we don't know so far in a rotational system. So try examples with that. And we will also solve some examples during the problem solving session. Don't worry about it. Okay, these are more or less equations for examples. Right. Nothing to teach here. Right. Another important concepts in while studying the first order, second order system, we will be see we have a system and we give some input and some output. So only with this, what we are going to do. So if I want to control the output, I am going with a closed loop system. Then if it auto corrects based on the output deviation, it's a good system. But even though with that deviation, some system won't be able to correct those deviations. Sorry, even with that closed loop feedback, some systems won't be able to correct its deviation. At that time, we need an external device called a controller. It sits in between the input and the system that monitors the change in the output and between the output and the input and makes some gains or generate some gains so that the output reaches the actual output reaches the desired output. So in order to design this controller, we need to know the feasibility first. Whether it is possible to define a controller for the system. Some systems, whatever controller you design, you won't be able to pull it to the finite value because if the system is naturally unstable, whatever input you give, even if it is a bounded input, bounded means it has some value, finite values. So it reaches this 10 or 100 or some finite countable values it will have. So this will give a unbounded output. It keeps growing exponentially. You don't know where it will stop and it won't stop whatever timestamps you fixed. For example, 100 iteration, 200 iteration, n iteration you run, it will just grow exponentially because the system is unstable. This nature of the system we want to find in order to design a controller first. That's how the stability comes into the picture. So first we are interested in the stability of the system. Only if the system is stable, we will be able to generate some reasonable commands to make the system work according to our needs, right? So that is the point behind finding the stability. Right. The system is stable if the system eventually comes back to the equilibrium state when the system is subject to an initial condition. We have to know the initial condition. So it has to come to a equilibrium state if it is stable. If it is unstable, it won't. It will just diverge and it will just grow exponentially, grow or decrease exponentially. It won't have any finite value to settle down. There is a in between sorry, between these two, stable and unstable. That is the marginally stable. This marginally stable, we cannot decide whether it is stable or not, but we can say at least for this time it will be stable. For example, it's marginally stable in the sense we used to define the left hand side as when you take a S domain, that is in real part and imaginary part. So whatever the area that covers the left domain, we say it is stable. So if the poles of the system lies in the left of the plane, we say it is stable. If the poles of the system lies on the right of the plane, we say it is unstable. We say whenever the poles is there, we say it is unstable. So this marginally stable case lies in between these two, in this region, in the imaginary axis. So it may go to unstable region or may come to stable region whenever there is a perturbation. We cannot decide. Only if the perturbation happens, then only we can say it has become stable or it has become unstable. So there are systems like that also. You cannot just cover everything under stable or unstable. There are systems that lies in between these two conditions. Those are called marginally stable system. We will study all those things in detail. Right. Now I said when I tell like whatever the system is, if I give a finite bounded input, bounded means some finite input. finite value, you know what value it is. So this we will get some output. So this bounded input is this one. So we have some bounded signal. A bounded input is a signal whose magnitude remains finite over all time. Mathematically, you can represent like this. This u of t, if I take a signal as u of t, it will always be lesser than some m value, which is lesser than infinity. This m won't go to infinity anytime. So the m is a finite bound. 10, it can be 10, 100, 50, 1000, lakh, but always it will be finite. You can count it using something, some known numbers. That's the explanation for a bounded input, bounded output. So if the system is stable, you would get the output as like similar to the input. Like it will also be bounded. Not guaranteed to be the same bound as in the input, but it will be bounded. Like finite, it will be finite. Then the system is stable. Otherwise, it's an unstable system. So this nature is called the Bibo stability. Whenever I am giving a bounded input to my system, if I get a bounded output, then I can say my system is a Bibo stable, bounded input, bounded output system. That's it. So if your input you are giving itself is unbounded, there is no point in learning what is the output of the system, right? That's the nuance behind this. So study this. It's a mathematical form of the Bibo stability and poles and zeros. So obviously, so when I try to connect this concept, see, um, this is energy storage elements. This becomes order. So poles, if I want to define in the same explanation, what is the highest order of your system? That becomes the number of poles of the system. For example, zeroth order system has 0 poles. First order system has 1 pole. Second order system has 2 poles. Similar, right? This orders and all we will do only from the denominator, right? The same thing. If I am connecting the order with that, for example, a square plus bs plus c. This is a second order system. So I can say there are 2 poles, or the system has 2 poles. So the poles directly connected to the highest order of the system. The number of poles, not poles, the number of poles is equal to the highest order of the system. For example, for this system, a is q plus b is square plus c is plus d, then this becomes third order system. Then it has 3 poles. Any doubt in this? So the energy storage element, order of the system, poles of the system, everything is same. If you have any doubt, please unmute and ask. Now, I want to say sq plus bs square plus cs plus d. So I can say there are 3 poles as the highest order of the system is third order system. Then what is 0? What do you call it 0? If this directly comes from the denominator, what else is there remaining? Numerator. So you look for zeros in the numerator. So highest degree of numerator will become the 0 of the system. We call it as 0. Highest degree of denominator, we call it as poles. So this will become 0 by pole. So 0 and poles will always be in Laplace domain. So Laplace of output by Laplace of input. This will become transfer function. So in a transfer function, the numerator, whatever values or whatever the factors of the numerator, numerator factors is called as 0. Denominator factors are called as poles. So the intricate part of a transfer function becomes 0 by pole. Transfer Laplace of output by Laplace of input. Is it clear? Anywhere it is confusing, just let me know. We will revisit that again. Any part of this is confusing? Will you be clear in order, energy storage element, and poles? Whenever I ask, will you be able to recollect this properly? Yeah, I hope so. If you have any doubt, just ask me. Please don't get confused. It's a very basics of control system. This we are going to build upon this over the next week of lectures. So when you go to root locus, Bode plots, so we will play around with these poles and zeros only. And stability majorly depends on these poles and zeros. Right. I hope it is clear. I'm moving with that belief that it is clear. Okay. So, for example, if I have a system S square plus S plus 1, right? So, what will be the factors of this? Minus b plus or minus root of b square plus 4ac by b 2a, sorry, 2a if you put. What will be the factors of this? I can say make it simple. S square plus 2s plus 1, no? It will become simple. 1, 1 will be the factors of this. So I can write it as s plus 1 into s plus 1. So just disintegrating the system representation into factors of the system. So that I can say this s plus 1 becomes s is equal to minus 1, s is equal to minus 1. So this value we call it as pole particularly. The factors of the system is being called as poles. So the system has two poles and the two poles lies at minus 1 comma minus 1. That's how we interpret it. Whatever the system is. So we draw it technically like if you want to visualize it, this is a 0 and this is the S domain j omega and this is a sigma. Whatever it is, sigma, right? Okay, whatever real part of the system. So we used to mention this poles as into mark like x. So there are two poles. We don't know how to differentiate it. Just make it dark, and there are two poles here minus 1. So this is the pole 0 representation of a system. Which system? 1 by s square plus s plus 1. This system. Sorry, s square plus 2s plus 1. Clear? So if I have some other system like s plus 2 and s plus 3, then its pole 0 representation will become, you have to definitely put this j omega and sigma, otherwise it doesn't mean anything. So this will become s is equal to minus 2, minus 3, minus 2, 1 into in minus 2, 1 into in minus 3. So this is the pole 0 representation of a system. Which system? 1 by s plus 2 into s plus 3 system. I can write it in terms of s square plus 5s plus 6. Right. So far I didn't give any zeros. Now I am going to consider one zero also. For example, the same system I am considering s plus 2, s plus maybe s plus 4, s plus 2 into s plus 3. Then the pole zeros will be s is equal to minus 4. Pole will be s is equal to minus 2 comma minus 3. So how I will write this? This will be minus 2, minus 3. 0 will be represented in terms of 0. Minus 4. So this is the distinguished version. Whenever there is a x, it represents poles. Whenever there is a 0 or a mark like this circle mark, it represents the 0 of the system. So you have to visualize that wherever this is, you have to identify this as a numerator. Wherever this is, you have to identify this as a denominator. Numerator and denominator. So if I just give this, Can you write the system from this figure? This figure. Can you write the system from this figure and type it in the chat box? Just type like this, sum like this, bar this. How will you represent the system? Can everyone please type the system if you understood properly? If if not, we will discuss on it. No problem. No need to worry about it. Just type the transfer function of this respective system and put it in the chat box. One has given s minus 8 by s plus 6 into s minus 5. Good. Prithvi also said s minus 8, s minus 5 into s plus 6. Very good. Yeah, that's the system. System is s minus 8 by s plus 6 into s minus 5. So this is the transfer function of the system where this represents a 0, this represents the pole, right? Now we are going to, now you are clear in what is 0, what is pole and how to represent the pole 0 representation. Now we are going to see the stability in terms of the poles and zeros. So when I write the Laplace domain, or when I draw the graph of the Laplace domain, whatever is there in the horizontal area, it's a real part, and whatever is there in the vertical area, it's the imaginary part that we know already from the Laplace transform understanding. Now I'm seeing if your pole, only pole, I'm not talking about zero right now, if your pole lies in the left half after the zero, that is, if your pole has negative sides, whatever value you take, but it has to lie in the negative side, it should be less than 0. So whatever value you take, I am considering this as stable system. So when the poles, 1 minute. Oh, sorry. So whenever your poles lies in near left half of the x-plane, it is considered to be stable. Whenever it lies on the, whenever your poles lies in your left half of the x-plane, it is considered to be stable left half. Whenever your poles lies in the right half of the x-plane, it is considered to be same poles, no need of zeros. It is considered to be unstable right of a. Keep this in mind. Why we do this, I will come to this later. I'll explain why it is. Okay. For example, if I have a symbol system, since I'm considering pole, I'm only taking a pole, not a numerator. I'm just considering a denominator. For example, if my transfer function is like this, so if I take an inverse Laplace transform and find a t domain, what will be the answer? So if you take a Laplace transform of 1 by s plus a, what will be? Will be e power a minus 80. Wait, I will have the same j omega theta. So I have a pole system that is 1 by s plus a here, 1 by s minus a here, because s plus a will lie here, s minus a will lie here, right? Minus a is c, because this will become s is equal to minus a, and this will become s is equal to plus c. So this is the poles of the system. For example, pole of system 1, pole of system 2, pole 2, pole 1. Right. Now I'm going to consider this both systems simultaneously. G1 of s is equal to 1 by s plus a, G2 of s is equal to 1 by s minus c. Now if I take a Laplace inverse and find a G1 of t, this will become e power minus at, because a Laplace of 1 by s plus a equal to e power minus at, Laplace of 1 by s minus a is equal to e power at. So this becomes G2 of t equal to e power at. Now g1 of t is equal to e power minus at, g2 of t is equal to e power at. When t tends to infinity, when it comes from 0 to infinity, how this both the systems will look like? G1 will look like this, something like this. G2 will look like something like this, you can say, because of e power at. Are you agreeing with me? Any deviations, or am I doing anything wrong? This is e power minus at, this is e power at. So as you can see, even it is from a infinite region, it comes to a finite point over a period of time. So it boils down to a finite point. For example, this is a finite point. At t tends to infinity, it has some 0 or 1 or some value, finite value it has. But here at t tends to infinity, we cannot hold up the value, right? It keeps growing and we don't know where it is going to yet. So this becomes finite, this becomes infinite. So obviously, based on the Bebo's ability, I am giving some finite input, and if I get some finite output, it's stable. Similarly, if I get some finite input, input will always be finite. Okay. If I get some infinite output, then the system is unstable, right? That's why we are saying this is unstable. Nothing is unstable, this is stable. So that's why we are saying, if you look closer, whatever there is in the right half of the explane, if your pole lies in the right half of the explane, for example a, this becomes e power at and this becomes infinite. So right half of the explane becomes unstable, left half becomes stable. So this is the stability of a system based on the pole location. Whenever you see only the pole will be responsible for the stability, zero won't add much. We will see some complex systems where zeros will, when the zero goes to the right half of the explain, how the system changes. It's a minimum phase, non-minimum phase difference. But for now, based on stability, so this is the nuances of the system. When the poles of the system or the denominator factor of the system lies in the left half of the S plane or half of the quadrants, like whatever negative values it has, then the system will be naturally stable. You can control the system. When the poles of the system lies in the right half of the S plane, it will not be stable, it will be unstable. You cannot design any controller to make it stable, at least for a linear case. Clear?
Yes, ma'am.
Okay. If you have any doubt, take a moment, go through this and ask me any doubt if you have. If you are clear with this, we can proceed with further things. If you have any doubts, please ask me. So from the definition, I want to revisit it one time. Poles of the system are the roots of the denominator polynomial. Zeros is the roots of the numerator polynomials. And for this is the zero, this is the pole of the system. So the zeros can be obtained from the numerator equation, poles can be obtained from the denominator equation. So zero will also be represented using z, and poles can be represented using p. Right? So this is the pole zero representation of the system. It was given about this system. So whatever we discussed so far, it's like this: s minus sk, and it can be written as a power e power at. If it is s minus a, it will become s is equal to a. When you write it, it will be e power at. So it will grow exponentially like this. And similarly, this is for real poles, and for complex poles also the nature is same, but it will just have some oscillation. Instead of going like this, it will go like this. That's it. For complex pole, it has some oscillation, but it settles for a poles having LHS. For example, if it presents here, if it presents here, so if it is here, it will have oscillation, but it grows exponentially. That is the difference between these two. So the imaginary poles, this is a special case I told, no. I have explained about stable and unstable, but I forgot about the marginally stable here. So this part, wherever there is a intersection, this part holds a special place. That is, this is called as marginally stable. This marginally stable system has imaginary poles, but it doesn't have any real parts, only the imaginary parts it has. So it will become plus or minus like this. It can be s plus j omega, and it will become s minus j omega. So the nature of the system will be oscillatory, but it is not any growing, or it won't be decaying. It will just oscillate at its place. So whenever there is a perturbation or from some disturbance, this may make this oscillation reduce, decay exponentially, or it may make the oscillation grow exponentially. So based on this marginally stable system may become stable or unstable. So it is based on the nature of the disturbance. So that's what we are telling. So if the poles lies on exactly on the imaginary axis, you would expect oscillatory responses. Similarly, there are cases with repeated poles, um, stable relationship with poles. If you can read this, whatever we discuss, it is explained here. See, this is the overall point of view you have to see. Whatever lies in the left half, it is stable. Right of it is unstable. On the imaginary axis, then it considered to be stable. Right half unstable. Whatever that lies in the imaginary axis, it is considered to be marginally stable. Poles, just speaking about the poles, not the zeros, because poles decides the denominator. Poles are in the denominator. Whenever we are writing a characteristic polynomial to find the root of a system, we use only the denominator. That's why poles decides the stability of the system. We have completed 3 lectures of it. We will just try to solve few problems, basic problems from this. Then we can improvise on those in later Wednesday or Friday class. So I will give few systems, and we are going to find whether the system is stable or not. Take pen and paper or use your iPad or whatever electronic devices you have. Try to find the stability of this system. One thing I want to insist is, instead of Okay, first find whether the system is stable or not. Tell me whether it is stable. Which one is stable or which one is unstable? Can you tell me which one of the systems are stable or which one are unstable? So I'll just write the expand version of this so that it will be easy for you to solve. S cube plus 2s square, c will be s square minus 2s, d will be s square plus 2s, right? So if I expand this again, I will get s is equal to minus 2, 1 pole. This will become, okay, s is equal to 0, 0, s is equal to minus 2. This will become s is equal to 0, s is equal to 2, s equal to 0, s equal to minus 2. Okay. Now tell me what are all the systems are stable, what are all the options are unstable.
Ma'am, so what happens if the pole is on the origin? Is it marginally stable or how do we consider that?
Consider it as marginally stable.
Okay.
It's on the imaginary axis, no? Origin imaginary.
Yes. Sir. So A is stable, B is unstable.
You are saying A is stable, B is unstable, okay? Can
Uh,
you say marginally stable?
uh,
Yes, ma'am.
two zeros, no, two poles on the origin.
Okay, right. So you are considering it as unstable. Okay, right. We'll keep it as, we can discuss on this.
Okay.
C is unstable.
C is unstable, right?
C is yeah, unstable.
D is
Marginally stable.
marginally.
Marginally stable.
Okay, since only one pole, everybody is agreeing with marginally stable, right? Very good. Thanks for the response. So the question, I haven't given one information deliberately. It's an open loop system. Whenever we are finding the stability of a system, we would consider the stability of a system of a closed loop systems. So whenever it was deliberately mentioned in the question, unless or otherwise, it will be open loop system. So sorry, if it is an open loop system, they will mention it in the question. Okay, so you have to find the closed loop system first, then you will have to find the position of the poles. Proceed to find the position of the poles. Now if I find the, we will try finding the closed loop system first, then we will do the same thing again. We'll compare the open loop nature and the closed loop nature of the system. Now how will you find the open loop closed loop equation? I consider everything will be the negative feedback system, unity negative feedback system. So it will become g of s, r of s minus plus y of s, h of s, right? So this is a negative feedback system. The overall closed loop transfer function gc of s will become g of s divided by 1 plus g of s into h of s, right? For the first system, a equal to, a is the, I will just rewrite it. A will be 2 by, sorry, 2 by s plus 2. B is 2 by s square into s plus 2. C is 2 by S into S minus 2, right? Um, D is 2 S plus 1 by S into S plus 2, right? I hope it's correct. Now if we find a closed loop system transfer function, it will become 1 minute. Sorry again. Okay, this is a open loop systems. So I want to find a closed loop system transfer function. From this I will write it 2 by g of s divided by 1 plus g of s into h of s. H of s is always 1. It's a unity feedback. So this will become s plus 4. I will write. If it is wrong, please let me know. This will become s square plus s cube plus 2 s square plus 2 it will. S cube plus 2 s square plus 4. Okay, this will become 2 by x square minus 2s square minus 2s plus 2. 2 into s plus 1 divided by s square plus 2s plus 1 plus 2s plus 2 become s square plus 4s plus 2. Right. Please let me know if you have any discrepancies with this, whatever I found out. I might be wrong. Don't rely on whatever I solved. Solve by yourself. I'll give 1 minute and let me know if it is wrong. I think I made some mistake. This will become 2s square. No? Then if I write it 2 by s cube plus 2s square divided by 1 plus 2 by s cube plus 2s square. It's correct. That's plus 2. Plus 4 I have put, right? Please solve by yourself. And this will become.
Yes, ma'am.
It's correct, right? S into s plus 2 by s square plus, sorry, minus 2s divided by 1 plus 2 by s square minus 2s s square minus 2s plus 2. That's correct. And that's also correct. Now tell me the poles of the system. Then this will become s is equal to minus 4. This will become s cube plus 2a square plus 2 equal to 0. I put found? You can use calculator if you want. Okay, when I found it was something like this: minus 2.3, 0.17 plus 0.9j, 0.17 minus 0.9j. So these are three roots for this. For this, it is easy. If you found any deviation, let me know. Okay? Wait. Minus 2, I don't come right. Minus b plus minus 2 of b square minus 4ac. Again, it is 0. Minus 2 mutation. Missing anything?
The system C, the roots are 1 plus or minus j. No?
It will be 1 plus or minus. Everybody is getting that big 1 by 2 is there, no?
Yes, ma'am. 1 plus j and 1 minus j.
Oh, it will be minus b will become minus 2. Then it will become 1. Okay. For the fourth one,
Minus 2 plus or minus root 2.
okay. Minus 2 plus or minus root 2. If you wait, just
J is not there, I think.
wait, just root 2, right? Okay. Right. No, if everybody is getting this, we'll proceed with this. Now we'll find whether this is stable or not. This is stable.
Yes, ma'am.
Yes, ma'am.
This will become
Unstable.
unstable. This is stable.
Unstable.
Oh, yes, ma'am.
This will become
Oh, no, no. Unstable.
this will become stable,
C
right?
is, no, no, C is 1 plus or minus j.
Oh, 1 plus or minus j. Okay. Then it will become unstable,
Yes, ma'am.
right? So
Yes, ma'am.
now I will just put a system 1, system 2, 3, system 4. Okay. And this will become open loop, become closed loop. So from the open loop transfer function, whatever we found is first one is stable, unstable, unstable, marginally stable. Sorry, stable. We'll consider it as unstable itself. Okay, stable and unstable. Right. This is marginally stable. In the closed loop system, we found stable, unstable, unstable, becomes stable. Now, can you understand the importance between the open loop and the closed loop system? Because open loop, if you give an input and you are getting a system and have an output, you don't really have any control or any knowledge about the system. But in closed loop, you have a little bit knowledge, even though it is not as good as putting a controller over the system. For some simple system, this putting a feedback itself is okay. This itself will correct the marginally stable to stable. This can pull the system from the marginally stable region to the stable region. So this is the beauty of the closed loop system. So, but it comes with a cost that you have to put more effort. Control effort will be more, but that's okay. Our ultimate purpose is being satisfied. So this is the this I want to you to learn that the difference between the open loop and closed loop system. So the point takeaway here is whenever the question is being asked about the finding the stability, look for a keyword whether the system given in the question is open loop or closed loop. If it is open loop, find closed loop system, then find the stability. Okay, this is some catch that make you lose mark. Right. I guess that's it. We can solve few other problems in upcoming sessions. If you have any doubts in today's sessions, you can ask. Feel free to ask. We can
Ma'am,
try
if
to
in the if in the question is not mentioned, it is a closed loop or open loop, then we assume it is a closed loop, right?
Uh, then it is little bit catchy because if they have given it like this, for example, CFS by YFS, sorry, CFS by RFS or YFS by RFS, then this is a closed loop system because transfer function of output by transfer function of input, then it involves the feedbacks and it is a closed loop system. If they have given GFS, then it is a open loop system. It's only the transfer function of the system. And if they want to find the closed loop system, they will mention whether it is a negative feedback. Sometimes we may want to assume, but in this question to find the stability, they will give whether it is negative feedback or positive feedback. If you have given GFS, they will give what kind of feedback, then you have to understand, you have to find the closed loop system. Otherwise, if they have just given find the stability of the system and has given CFS by RFS, then it is a closed loop itself. You don't want to find a closed loop again. Just these two. If they have given GFS, they will give feedback. Otherwise, they will give it like this. This is a closed loop system. You can proceed with this. Otherwise, you have to find the closed loop here and then have to find the stability.
Okay, ma'am.
Ma'am, if they give positive feedback means we have to assume.
The transfer function you are finding should be based on this
Okay.
for positive feedback. Now we have assumed G of S by 1 plus G into H now for negative
Yes, ma'am.
feedback.
Yes,
Just
ma'am.
change this into the transfer function and find it.
Okay.
And but we won't give positive feedback at all because that doesn't make sense. Positive feedback doesn't give any stable system. It will give the oscillatory system. There is no
Okay.
in asking find the stability. But I am giving this for a general point of view. If someone has given positive, just go with this transfer.
Okay.
Okay. If you don't have any questions, we can wrap up the session. I'll put the live session link. But this session will take some time to render. I will update it during night. But the previous session I will upload and give the link. Thank you so much for joining. You can leave if you want.
Thank you.
Thank you.
Thank you, ma'am.
Thank you.